Good evening to all. So this is our 25th lecture session of the course, Computational Fluid Dynamics. In the previous lecture, we have started with broad topic of FBM-based discretization of Navier-Stokes equations, and in particular, now we are referring to one of the technique for finding out the solution of Navier-Stokes equation using computational approach, and that particular technique is something which is referred to as simple algorithm. Okay, where simple is nothing but semi-implicit scheme for pressure linked equations. Okay, so in our last lecture, I told you that we require initially, in case of simple algorithm, we start with some initial guess for the pressure and velocity fields, and while we substitute these guessed fields, we get some value for the velocity field, but that is corresponding to the initial guess. That is not accurate. Okay. Then we have defined some terms P dash, U dash, and V dash as the correction terms to our velocity field. And after applying these corrections, nothing but we will be getting our accurate fields. Okay. And after defining these correction terms, then we have got some equations. We have got some equations for our correction terms, which relates the velocity corrections with pressure corrections. And then in these two correction equations, we had applied Patankar's approximation, which suggested that for all the neighboring nodes and their coefficients, sum of all the neighboring nodes in both horizontal as well as vertical directions, we will be taking summation equal to 0. Okay. Then if we substitute these approximations into our main equation, then we found that Aij into U dash I comma j is nothing but equal to P dash I minus 1 comma j minus P dash ij into A of ij. Okay, so this is the relationship in between velocity correction and pressure correction for x momentum equation. Similarly, we have found relationship in between velocity correction term and pressure correction term for our vertical component of the velocity. Okay. So, by using these correction terms, nothing but if we know any one of the correction, either velocity or pressure, we will be able to determine the correction term for the other. Okay. So, what we will be doing, basically, in these equations, we have to first determine the pressure correction term, and that pressure correction term will be helping us in finding the values for U dash and V dash. Okay, so now here comes the question that how to determine the pressure correction term. Okay, so this is one very, very important question now. So can you tell me how we can proceed for finding out this pressure correction term? Any idea you are having? Any one of you?
Sir, through the continuity equation, somehow relating velocity with pressure.
Yes. So this is one important aspect, that till now, whatever these two equations we are writing, these are derived based on the x momentum equation and y momentum equation. Okay. However, when we have to solve the flow of the fluid, there is one more equation which we have to satisfy. And what is that equation? That is nothing but our continuity equation. Okay. So discretized form of continuity equation is something which we have not yet written. Okay. So now if we consider the incompressible and steady flow situation, for that continuity equation will be becoming del by del x of rho u plus del by del y of rho v equal to 0. Okay. Now this continuity equation, in this continuity equation, when we will be substituting our pressure correction terms, we will be finally finding that this equation will take the form of nothing but our pressure correction equation. Okay, and so considering that, what we will be doing now, while we will be discretizing this particular continuity equation, this we will be discretizing over nothing but our scalar control volume. Okay, so the discretization of this particular continuity equation now we will be doing for scalar control volume. Why? Because when we will be substituting the different velocity terms, this equation will finally give us nothing but pressure correction equation. Okay, so this pressure correction equation will be actually finally the resulting outcome of this particular continuity equation. So that's why we want to discretize it over our scalar control volume. Okay, so what we do when we have to discretize, nothing but we consider integration over the control volume. So I will be doing del by del x of rho u over my control volume. Say I have to do volumetric integral, and this I have to do over the scalar control volume. So I am adding s as subscript. Okay, plus I have to do integral del by del y of rho v, and this also will be volumetric integral over the scalar control volume equal to 0. So let me write scalar control volume as v bar s. V bar s. Okay. So now can you tell me what I will be finally getting after applying the Gauss divergence theorem? So after applying the Gauss divergence theorem, I will be finding sum of rho u into AFX and areas in x direction plus sum of rho v into AFY into, this has to be considered over all surfaces along the y direction is equal to 0. Okay, now I told you that this integration we are doing nothing but over our scalar control volume. Now let us try to see, when we will be considering the scalar control volume, what will be our indices corresponding to different phases. Okay, so let me go back to our grid structure which we have drawn earlier. Okay, so now this PC is a little bit slow. I think it will take time to reach back. Yeah, so now can you tell me which one is our scalar control volume and what is the node point corresponding to scalar control volume?
Capital I, capital J.
Yes, capital I comma capital J is node point corresponding to our scalar control volume. So that's why now this boundary, whatever I am showing over here, that will be becoming part of scalar control volume. Okay, so you can see now in the x direction I am finding two faces. This is my east face and this is west face. Okay, can you tell me the indices for east face? It is
Small I plus 1 J.
small I plus 1 comma j, and in the west direction it is small I comma j. Similarly, if you see, this is our north face, this is our south face. So for the north face, our indices are here. It will be, if you see, it will be, I will be remaining as it is. Okay, and it will be small j, and this point will be, sorry, it will be small j plus 1. Okay, and this bottom point in the south face will be capital I comma small j. Okay, this point is clear to everyone?
Yes, sir.
Okay, so let me go back and now write the corresponding indices. Okay, so I can write that rho u into A at point, which point? Small I plus 1 comma capital J, is this correct? Minus rho u A at small I comma capital J plus rho v A at point capital I comma small j plus 1 minus rho v into a at point capital capital I comma small j equal to 0. Okay, so this is something which we have got. Now we know already some equation. We have found that u is nothing but equal to u star plus, what is the value for u? U star plus u dash, and v is nothing but v star plus v dash. Okay, here u dash and v dash refer to as the correction terms, and u star and v star are the values of velocity corresponding to the guessed pressure, and u and v are actually our accurate velocity fields. Okay, now when I will be referring my velocity field corresponding to point, so I have to estimate now velocity field for all the points small I plus 1 comma j. So here I have to calculate u, then at point small I comma j also I have to estimate u, and v I have to estimate at capital I comma j plus 1 and capital I comma j. Okay, so if I estimate u, let us first consider the point small I comma j, that will be equal to u star at point small I comma capital J plus u dash at point small I comma capital J. Now if you go back, just I have shown you in the previous slides that u dash is nothing but equal to, what is the value for u dash at point I comma j? P dash capital I minus 1 comma j minus p dash I comma j into aij. Okay, so now I will be using this particular substitution for my u dash term. Okay, so I will be finding finally, when I will be substituting the value for u dash, I will be finding u star at point I comma j plus, can you tell me what I will be getting? Please tell me.
P dash capital I minus j.
Capital I minus 1 comma j. Yes.
Minus P dash I capital I comma capital J into a small I j divided by small a I comma capital J. Small I.
Okay. Now let us call this capital A I comma j divided by small I a I comma j as some another coefficient d I comma j. Okay. So what I am doing, I am calling this as some another coefficient. Okay. So if I do so, I will be finding that u I comma j will be equal to u star I comma j plus d I comma j times p dash I minus 1 comma j minus p dash I comma j. Okay. Now another term I want to calculate in horizontal direction is nothing but u at point I plus 1 comma j. Now can you tell me similarly what will be the value for u at point I plus 1 comma j? Please tell me.
Sir, P dash I comma J, P dot minus P dot I comma J.
I plus 1 comma j. Okay. Now let us find out the components of velocity at point capital I comma j plus 1 and capital I comma j, vertical components. Okay, so v will be equal to at point capital I comma small j as v star at point capital I comma small j plus, let us consider that coefficient I will be getting as nothing but d at point capital I comma small j. What I will be getting inside, can you tell me? P dash at point
I comma J, capital J minus 1 minus capital I, comma, capital J.
Okay. Then similarly, I have to calculate V at point I comma j plus 1. That will be V star at point I comma j plus 1 plus d of I comma j plus 1 times e dash I comma j minus p dash I comma j plus 1. Okay, so I have obtained now the different the equations for these different values. Now what I will be doing, this is my main equation. Let me call it as, say, equation number 1. So in this equation number 1, now I will substitute the values of these velocity components. Okay, so if I do so, I will be finding 1 as rho u times, sorry, rho into a times at point I plus 1 comma j, and what I'll be getting in the multiplication, please tell me, otherwise I have to every time go back to the previous slide. Please tell me. U star at point I plus 1 comma j plus d
I plus 1 capital J
multiplied with
P dash capital IG
capital IJ
minus P dash capital I plus 1G.
P dash capital I plus 1 j. Your voice is coming very less, I think. Someone is speaking. Who is speaking? Your voice is coming very, very less. Please speak closer to the microphone. Let me check here. Okay. So, then what will be the next term? Please tell me.
Rho A, small I, J, capital J, into U star, small I, capital J, plus D, small I, capital J, into P, I minus 1, capital J, capital
Have
I.
I written it correctly?
Yes, sir.
Okay. Plus rho times A capital I comma small j plus 1 times V star capital I comma small j plus 1 plus d times capital I comma small j plus 1 times p dash of I comma j minus p dash of I comma j plus 1. Is it correct?
Yes, sir.
Minus rho a I comma small j times V star I comma j plus d capital I comma j times p dash of I comma j minus 1 minus p dash of I comma j, and this entire will be equal to 0. Okay. Now let us segregate these u star as the separate terms and all other terms as the separate quantities, and we will try to keep these indices p dash I comma j and p dash I plus 1 comma j as nothing but we will segregate based on the pressure indices. Okay, so one important thing I will be getting, let me first write down all the u star and v star terms. So if I write down u star and v star terms, I will be getting rho a times I plus 1 comma j into u star at I plus 1 comma j minus rho a times I comma capital J plus, sorry, here I will be having u star at I comma j also, okay, plus rho a into v star, and this entire I will be having at point I comma j plus 1 minus rho a into v star, and this will be at point capital I comma small j. Okay, so this is one term. Then plus, let us now segregate the terms involving p dash ij. So I will be writing outside p dash ij. Now please tell me what will be the coefficients of p dash ij. So from the first, I will be getting coefficient as rho a into d. Is it correct?
Yes, sir.
Rho a into d at point I plus 1 comma j. Okay, then from the second equation, if I see, it will be minus once again plus, okay, this minus and this minus, so it will be rho a d at point
Small I, capital J.
small I capital J. Then I will be having plus rho a d corresponding to point capital I small j plus 1, and then I will be having plus rho a into d corresponding to point capital I comma small j. So these are the coefficients of p dash ij term. Okay. Now apart from this, we are having one individual terms, and for them the coefficient will be. So let me start with the first one. So in the first one, I am having p dash I plus 1 j, and it is with negative sign. So let me write minus p dash I plus 1 comma j, and its coefficient will be rho a d into rho a d at point I plus 1 comma j. Okay, then we have another term over here as plus p dash at point I minus 1 comma j, and its coefficient will be rho a into d at point small I comma capital J. Okay, then after this I am having one more term as minus p dash I comma j plus 1, and its coefficient will be rho a into d at point capital I comma small j plus 1, and then I will be having plus p dash at point I comma j minus 1 times rho a d into what I will be getting at point capital I comma small j, and this will be equal to 0. Till this point it is clear? Is
So
this equation?
last and third last term should be negative.
Last and third. Okay, yeah, let me write it. Yes, outside there was negative sign, so it will be negative, and this will also be negative. Yes, yes. Okay, so this particular equation is something which is known as pressure correction equation. Why we call this as pressure correction equation? Because you can see this is nothing but an algebraic expression, and in this algebraic expression, if you see this first term inside the square bracket, this is something which is already known to us. Can you tell me how it is known? How this term is known to us?
Prior value of
Yes, because it is involving all the star values, and star values are actually obtained corresponding to the guessed value of the pressure. Okay, and apart from that, it is having p dash ij. So p dash ij is the node at which we are actually calculating the pressure correction, and that is becoming function of nothing but surrounding nodes of the scalar. Okay, so surrounding scalar nodes which are involving p dash. So here in this particular equation, each and every term is nothing but each and every unknown is actually nothing but p dash. So this particular equation is something which is referred to as pressure correction equation, and this is obtained from our continuity equation. Once we substituted over here the relationship in between the velocity and the pressure correction. Okay, now once we have obtained these velocity corrections, once we have obtained this pressure correction term, we will be substituting back and we will be easily able to find out our velocity correction values. Okay, and once we have found all our corrected values, p dash, u dash and v dash, I can easily find out accurate pressure as nothing but p star plus p dash. Then I can find out accurate velocity, horizontal velocity field as u star plus u dash and vertical velocity as v star plus v dash. Okay, so overall idea is clear how we are processing. Whatever I have told you till this point, it is clear to all?
Yes, sir.
Okay. Okay, now here comes one important point. Okay, so basically what we are doing, initially we are taking some guess and then we are finding some correction term in order to correct our velocity field. Okay, in order to correct our pressure field and then our velocity field. Now can you tell me what will be happening if our initial guess is not good? In that situation, what will happen if our initial guess is not good?
Correction will be large.
So if our initial guess is not good, in that case the p dash term will be very large. If p dash term is large, it means our entire solution will be dominated by p dash. Okay, so it means if p dash is large, our entire solution will be dominated by p dash. If it is dominated by p dash and say somehow we have actually got some issues with our initial correction term p dash, so what will be happening? Our solution will be actually becoming unstable. Okay, so large pressure correction term sometimes may lead to oscillations into our solution. It may lead to instability. Okay, and it may also happen that sometimes our solver will not at all converge. Okay, so it will be diverging while we will be processing, while we will be further progressing with the iterations. Okay, so this is one important consideration, that if our initial guess is not good, in that case our pressure correction term p dash will be very large and our entire solution will be dominated by the pressure correction term, and there will be chances of divergence of the solution in certain cases, and if it is not diverging, it may happen that our solution will become unstable. Okay, so that's why what is basically done to decrease the effect of this initial correction p dash, we use some additional coefficient, and that additional coefficient is something which is known as under relaxation factor. This point is clear?
Yes, sir.
So what we are doing, we are now introducing some new factor. That particular factor we are calling as under relaxation factor. Why we are introducing that under relaxation factor? Because it may happen that if our initial guess is not correct, then this pressure correction term will be having very large value and it will be dominating the entire solution, and sometimes the dominance of this correction term into the solution may lead to instability and even divergence of the solution. Okay, so what we do, we introduce some under relaxation factor which is given by a symbol alpha p, and instead of using the correct pressure as p star plus p dash, we define our new pressure as nothing but P star plus alpha P times into P dash. Okay, so this value of alpha P, if it is equal to 1, in that case it means we are giving 100% weightage to our pressure correction term, and if we keep alpha P equal to 0, in that case we are not including our pressure correction term into the solution. So generally what we do, the value of alpha is actually selected in between 0 to 1. Okay, so for general solution procedure, value of alpha is selected in between 0 to 1. Now there are two implications. If our alpha P is approaching to 1, that will be helping us in fast convergence of solution. Okay, fast convergence of solution. However, there may also be chances of unstable solution. Okay, and when alpha P is approaching to 0, then our solution will become stable. So solution will become stable, but there will be chances, so there will be actually slow convergence. Okay, solution will become stable, but there will be slow convergence because we are using very small fraction of the pressure correction term. So if we are using a small fraction of the correction term, it will be taking more number of iterations to reach to the converged solution. Okay, so this is one very important term, pressure correction term. Similarly, as we introduce the pressure correction term, this under relaxation factor for pressure correction term, similarly we also have some under relaxation factors for velocity term also. Okay, so generally what we do, we use alpha U and alpha V as velocity relaxation factors. And how we use these velocity corrections, what we do, we say that our new velocity will be nothing but alpha U times of U plus alpha plus 1 minus alpha U times of U at iteration n minus 1. Similarly, V new will be equal to alpha V times V plus 1 minus alpha V times V at iteration n minus 1. So what is the meaning of this? When we are estimating the value of new velocity at any iteration n, we are giving the weightage whatever velocity, correct velocity we have got from that iteration, that we are multiplying with some under relaxation factor, and we are giving some weightage to the correct velocity, to the new velocity which is actually obtained from the previous iteration. Okay, so what we are doing, we are not putting our entire dependence on the iteration step, actually on a single iteration step, rather we are linking our solution to the previous iteration step also. Okay, so in this type of situation, what will be happening, our solution will be depending upon whatever is done in the previous steps also. Okay, so if anything is going wrong in a single step, that will not lead to significant issues into our solution, because along with that particular iteration level, we are also giving weightage to the previous steps. Okay, so similarly, for this velocity under relaxation factors also, values varies from 0 to 1. Till this point it is clear?
Yes, sir.
Okay, now let me introduce you that if we are using these relaxation factors into our solution, then how our discretized equation will be affected. Can you tell me how our discretized equation will change? So what I am saying, U at new iteration is nothing but equal to U correct velocity field at that iteration level plus 1 minus alpha times correct velocity from previous iteration level. Okay, so now if you see this particular u, what is the expression for this particular u? Can you tell me? The expression for this particular u is nothing but summation of a and b into u and b plus p at, so say if this u I am calculating at point small I comma j, so I have to divide over here with coefficient small I comma capital J plus p at point I minus 1j minus p I comma j divided by a ij times a into ij plus bij. Have I written it correctly?
Yes, sir.
Okay, so this is nothing but velocity at the iteration level where we want to calculate it. Okay, so from here, if you want to calculate u new, what will be the expression for u new? So I can say that u at point
Sir, what is bij?
bij is source term s bar into delta v bar u.
Okay.
Okay, so now I can say from here that my u at point I comma j, so that is my final velocity. If I consider the under relaxation factors, my final velocity at point I comma j will be nothing but alpha u times, now I will be substituting this expression, alpha u times summation of a and b divided by a I comma j into u and b plus this I have to write in bracket plus p at point I minus 1 comma j minus p at point I comma j times a ij divided by a I j. Okay, and moreover I have to include one more term plus b I comma j. Okay, and then I will be writing plus 1 minus alpha u, and while I will be writing this 1 minus alpha u, obviously I have to consider this coefficient aij over here also, so I will be writing 1 minus alpha u divided by a I comma j times u power n minus 1. Okay, so now this is my new actually discretized equation for correct velocity field. If I include my under relaxation factors into the consideration. Okay, similarly, can you tell me what will be the equation for v capital I comma small j? What will be equation for v capital I comma small j? Please tell me. It will be alpha v times sum of a and b divided by
Capital I, small j.
a capital I small j into v and b plus
Plus P capital small I. This is capital I, j minus 1 minus P capital I capital J into a capital I small j divided by small a capital I comma small j plus b terms, sir.
plus b times
P
capital I comma.
small j.
Okay, and with this also I have to divide with a capital I comma small j. Probably I have missed in the previous slide.
Yes, sir. Yes.
So here also I have to divide with small I comma capital J. Okay, and then I will be having plus 1 minus alpha v times divided by a capital I comma small j into v power n minus 1. Okay, so this is now my new equation. So from here you can clearly see earlier when I have estimated the values for d, what was my d? I have estimated d as nothing but from the expression of uij, and my d was aij divided by small a I comma j. Okay, so if I use under relaxation factors, my definition of d small I comma capital J will become alpha u times a small I comma capital J divided by small I comma capital J. Similarly, definition of d capital I comma small j will become alpha v into a capital I comma small j divided by a capital I comma small j. Okay, so my definition of d will also change, and if the definition of d is changing and expressions for u and v are changing, that will be actually modifying our pressure correction equation also accordingly. Okay, so whatever, when we will be substituting these values into my discretized form of continuity equation, that will change my coefficients of pressure correction equation also. Is this point clear?
Yes, sir.
What about others? So whatever just now I have told, is this clear to all? So what I told that I have
Yes, sir.
told. Okay, fine. So if we use under relaxation factors, then how our coefficients will be actually modified in the different equations. Okay.
Sir,
Now,
screen is looking black.
now is it coming?
Yes, sir.
Okay. Now, let me tell you that as I told you that it is nothing but an iterative loop. So when we will be doing and progressing the different iterations, at what point we have to stop the solution. Okay, so that let me explain you. So what I will be doing now, I will just give you the different steps for simple algorithm. Okay, so what are the steps, how we have to proceed the solution? What will be the first step? Can you tell me what will be first step over here?
Guessing P.
So we have to initially guess U, V and P, and these guessed values will be becoming nothing but U star, V star and P star. Is this point clear? Sorry. Yeah, so these are our initial guessed values. Can you tell me why I have initially guessed U star and V star, or U and V also? Why I have guessed U and V?
For the correction of P.
Yeah, so we will be using U star, V star into our, for the correction of P, we will be able to calculate from momentum equation. But before that, while we will be solving the X momentum equation, that will be involving coefficients as nothing but, what are the coefficients?
Yes, sir. Yes.
There are some dependence on neighboring nodes also. Okay, so that's why we will be first guessing all our velocity field and pressure field. Okay, and corresponding to that, whatever the pressure we will be getting, that pressure we will be calling as P star. Then after that, what is the second step? Solve X and Y momentum equations. We have to solve X and Y momentum equations using gas pressure P star.
Why have you dropped the star sign in U and V?
Yeah, let me put it over here, no problem. Yeah. And obtain what we will be obtaining when we will be solving the x and y momentum equation.
U and V.
But these will be nothing but my U star and P star, because these are corresponding to the gas pressure P star. Okay.
But sir, same notation has been taken for the earlier guessed values of U and V.
Yeah. So what I am saying, say in the initial domain, you have defined some values. Okay. Now, when you will be referring to first node, you will be using these values, and you will be obtaining some new value for this one. Then when you are going for this, you will be using these as the prior known values, and then you will be finding some new values. So these U star and V star are corresponding to the new values. Okay.
Okay, sir.
Then what is the third step?
Correction for Q.
Now we have to solve pressure correction equation. What pressure correction equation will do? It will give us value of P dash. Once I have obtained P dash, what is the next step? Correct velocities. Fine. So from here I will be getting the value of correct U and V. Once we have got values for correct U and V, we will be stopping, or what we have to do?
Sir, P also.
Yeah, U, V and P. Yeah, what we will be getting after that?
So repeating the same till the convergence is achieved.
So after that we will be doing check for convergence. What do you mean by convergence? Can anyone tell me what is the meaning of convergence?
Till the computed fields are falling under our tolerance value that we have specified.
Yes. So basically what will be happening, once we have found the values of U, V and P, we can substitute these values of U, V and P into our discretized continuity and momentum equations. Okay. When we will be substituting these into our discretized continuity and momentum equation, we will be having some value on left hand side of the discretized equation and some value on right hand side of the discretized equation. Okay, because we are over here finding the approximate solution, so we are not actually having exact solution. So that's why we will not be having always left hand side exactly equal to right hand side. So we will be having some difference between the left hand side and right hand side. So the difference between left hand side value minus right hand side value is something which we call as nothing but residual. Okay, this point is clear. And if this residual is less than equal to some specified limit, in that case we will be calling that our solution has converged and we will be stopping the solution. Is this point clear? Please say yes or no. Do I need to elaborate again? Do I need to explain this point again, or is it clear to all?
Clear, sir.
Okay. Now, let me tell you one more important point. So, when we are having this simulation domain, so inside the simulation domain, we will be having large number of nodes. Okay. Now, it may happen that for one node, say when you are using the continuity equation, for one node you are getting residual as RC1, for other as RC2, for third one as RC3. Now tell me which residual you have to satisfy.
Maximum.
So what we do, we calculate total residual for continuity. Okay, and total residual for continuity will be nothing but summation of all the residuals. Because please mute your microphone. So that will be becoming sum of all the absolute residuals. Okay, so let me write it as, say, RC sum P, and this summation I will be doing over all the nodes P, and this value of P will be going to maximum number of nodes whatever we are having. Okay, so whatever the total absolute residual we will be having, so it may happen that some of the residual we are getting as negative sign. So this positive and negative may result in zero value. So that's why we don't consider sign over here. What we do, we estimate the total residual for our all the nodes, and if that total residual is less than equal to some specified limit, then only we say that our solution has converged. Okay, so those of you who are already doing the simulations using any of the CFD software, say OpenFOAM or ANSYS, you might be aware that you get some residual plot. Okay, so that residual plot is nothing but it is something like this. Here you are having number of iterations, and in this side you are having some residual. So it is, say, 0, 10 to power minus 1, 10 to power minus 2, something like this. And then you find that you are having some values something like this. Sorry, this is not 0. So this is 10 to power minus 1, minus 2, something like this. So you find that you are having initially very high residual, and then there is some drop in residual, something like this. And if you are doing two-dimensional steady solution, you will be finding one residual for continuity equation, okay, one residual for x momentum, and one residual for y momentum. And when all these residuals go below certain specified limit, then we call that our solution has converged. Generally, we consider, for most of the flow situations, we consider 10 to power minus 5 as our convergence limit. Okay, but it is not very specific. This is something which depends upon the flow situation and the type of problem we are solving. Okay, at the same point of time, whatever under relaxation factors I have specified, I told you about the advantage of and limitations of high and low under relaxation factors. So under relaxation factor is also something which is not very specifically known, that what is its optimum value. So what we have to do, depending upon the type of problem, we have to try different under relaxation factors and then find that which one is serving our purpose better. Okay, so this is the overall idea about the simple algorithm. Now I will stop at this point, and we will have further discussion in our next lecture. So if you are having any queries, that you can discuss now.